Is this okay? This doesn't feel okay. I'm sure it's okay. Let's just keep going. Hello Internet, my name is Quinn, and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive build this week, and it's time to finish the major construction on the boiler. We've got all the stay bolts to do, and a bunch of intricate work in and around the firebox, and of course that front tube sheet. Lots to do, should be really cool. Let's go. Here's the current state of the boiler. It's looking pretty decent, but we've got a fair chunk of work to do yet. The next job on the list are the stay bolts. Stay bolts are reinforcing structures that go through double-walled flat sections of boilers, like this area of the firebox here. You got to support both double-wall sections there, tie them together, because flat surfaces can't handle pressure. On a real boiler, stay bolts look more like this. There's a lot of them, very, very close together, because you really can't have any amount of flat surface that isn't supported by something else on the far side of it. For model locomotive builders, the challenge with stay bolts is that they're a very difficult structure to silver solder. Because there's so many of them, it's a lot of little sources of leaks. Furthermore, they're always inside the firebox and in other inaccessible areas. So stay bolts are one of the #1 issues. Now, Kozo's design is pretty clever in this area. In order to make this as easy as possible for you, his stay bolts have large flat heads on them, which is unusual. And that means he can use a lot fewer of them because each stay bolt is supporting a larger area. So it's only 6 stay bolts on each side of this flat area, which makes it about as easy as stay bolts can be. I'm going to start over on the mill here by drilling a hole for the first stay bolt. I'm going to get the side of the firebox basically level there, square with the mill as best I can. This isn't super critical, but the flatter this surface is, the straighter the stay bolts will be, and the better the heads will seal on the surface, so it's worth spending a little time on this at least. The boiler at this stage is actually quite easy to fixture, which is a relief from some earlier stages. There's so much structure in it now that it's really very strong, and you can clamp down on it pretty firmly. I'm squaring it up to the edge of the table here because I want the square pattern of stay bolts to be reasonably attractive looking. And I'm finding one corner of the firebox edge there with the edge finder. And then I just did a little dry run with a Sharpie mark to make sure that the bolt pattern looks about correct. This bolt pattern is visible when the locomotive is done, so I want it to look nice. And of course I need the stay bolts to be in the correct place. They're biased towards the top there, as you can see, in order to give support up higher because the foundation ring does a good job of supporting the bottom edge of the firebox. And away we go. I started by center drilling the first spot. And I'm going to drill through, and this was almost physically painful for me. This was like drilling a hole in my child. I'm not going to lie, after all the work that's in this thing, I don't want to start drilling holes in it, but it's necessary in order to pump my child full of high pressure steam. Alright, that metaphor kind of got away from me there, but you get the idea. Deburring those holes could be tricky, but I've got a secret weapon here. This is my Noga backside deburring tool. There's a link to this below if you're interested. What's cool about this thing is not only can you deburr the backside of a hole like this, but you can also use it to deburr holes that are inaccessible because they're in a double layer, just like this is. So I can sneak this tool in here, and I can deburr the back of the upper layer and the top of the lower layer. And deburring all this isn't super critical, so if you don't have the fancy tool, you can get away with not doing it, I'm sure. I'm going to make the first stay bolt next before I drill the rest of the holes, because I want to make sure all my dimensions are going to be good here. This is going to be an exercise in mass production, so I want to set up one prototype stay bolt that I know is perfect, and then I'll be able to use the numbers on the DRO to get the rest of them the same. I'm starting by taking the lightest possible cut that I can to clean up the OD. The stock is just slightly larger than the heads on the stay bolts need to be, so I want to remove as little as I can here just to get that to clean up. It looks like I'll be able to get that to clean up, but probably not this area here where there's these little kind of track marks here. These are from the gear tooth roller thing that pulls the stock through the dies when they're manufacturing this. Those marks are pretty deep, so I'm not going to be able to get those out, but that's fine because the head is very thin, so it's unlikely that those are going to cause any issues. With the OD established, then I turn the skinny area at the bottom that will form the threads and the shank of the bolt. And I'm using my DRO here as I go. This is going to be important in a minute, you'll see what I mean. But for this first one, I'm just establishing all of my dimensions. And once again, just making sure that what I'm going to end up with is going to be perfect. Then I do a finishing cut and I face that shoulder on the back. And let's see how I did dimensionally. And that is looking really good. So I'm going to set the diameter of my DRO right there. And then I'm going to turn down this area here at the base for the threads. I want clearance for the threading die. So I turn another 5 to 7 thou off that. And then I cut the threads here at the base. We need just the right number of threads. That's important because the threads need to stick through the bottom but not be too long. So I decided probably another half thread on there was in order. So I just wound the die up until I feel it start cutting again. And then I put another half turn on it, wind it back down. And that looks like that's probably about right, but we won't know till we test fit. And the threading die always chews up the end a little bit, so I'll chamfer that with a file. As I'm doing all these steps, I'm thinking about the mass production sequence that I'm going to be using here as well. So I'm kind of refining that in my head as I go along. Next, I find the end of the part with the parting blade, and I've got the DRO switched into incremental now. And again, more on this in a second. And I go through partway with the parting blade, just enough to give me clearance for the chamfering tool. The drawings call for a 30-degree chamfer on these, which conveniently is the same as a threading tool. So I'm just going to use my threading tool here. With this, I'm going in a little bit at a time, just until it looks about right. I don't have a dimension on this chamfer, but you can tell from the drawing kind of where it's supposed to end up. When I think it's correct, I note the value on the DRO again in my head, and I come back in with the parting blade, and I finish parting that guy off. Yahtzee. And I'll test fit this to see if this is going to be my prototype or not. The chamfer is a little too small, so I know I want to enlarge that. The length is the next thing I'm worried about. This has to be just right. It has to go through the double wall, and there has to be enough threads exposed to tighten the nut. And in fact, I need about another half thread there. I can see the shoulder above the threads, which means that the nut is not going to tighten firmly against the inside of the firebox there. So it actually took me another couple of tries to get one prototype that I liked, but now I can go into mass production. So here's how this works. I'm leveraging the DRO here for efficient mass production. The first tool is the turning tool, and for this the absolute scale is reserved. This allows me to turn the OD of the stock, then the shoulder of the bolt, and then the little turn down area for the thread, all without measuring anything because the X and Z axis are set appropriately for those dimensions on this tool. Then I switch to the incremental axis, and there the Z axis is reserved for the parting blade. That sets the overall length of the bolt, and the X axis is used for the chamfering tool, which measures the depth of the chamfer that I'm putting on the head. So rather than setting up all the tool offsets and so on, which you can do in a DRO, I'm just using the fact that I've got 4 axes across 2 different scales that allow me to use 3 different tools for each of the operations. And this works because, of course, the X-axis doesn't matter for the parting blade, and the Z-axis doesn't matter for the chamfering tool. Let me demonstrate here. So this all depends on starting in the same place every time, of course. So I always start with a faced surface, then I place the turning tool at 0 on the Z-axis on the DRO, and then I bring the stock out to touch the tool. And now I know I'm starting in the same place for each bolt. Starting on the absolute scale then, I turn the OD of the bolt overall. This is the largest diameter, which is the head. And I don't have to measure anything here, I just set the tool on X, the diameter that it's supposed to be, because I've already set up the DRO's values here for this on the prototype. Then I turn the shank of the bolt down, again just turning down to the correct value on the X-axis on my DRO because I've again pre-calibrated that. By calibrate, I mean you measure a machined surface and then punch that diameter into the DRO so the DRO now knows where the end of that tool is from then on. Finishing cut to final dimension, then I turn down the little threaded area and then I bring in the threading die. And the convenient thing here is because I don't have to do any drilling, the threading die here can just live on the tailstock throughout this whole production run. I compare to the prototype, make sure my thread depth is correct, and then I switch out to the parting blade and I switched to the incremental scale on the DRO. I move down to the correct distance for parting, and I part most of the way through the piece like so. Then I switch to the chamfering tool, and I line this up on the slot made by the parting blade. This I just do by feel, and then I feed into a predetermined value on X that I know is going to leave the correct chamfer, again determined by the trial and error on the prototypes. Then I can switch back to the parting blade, which I can easily get into the same groove, again because Z on the incremental scale is reserved for the parting blade. I position it back in the slot where it was, and finish the part. Yahtzee. Finally, I face off that surface lightly again to get a clean start for the next piece, and then I go back to where I set the tool on 0 on Z on the absolute, pull the stock out to touch the tool again, and do the next one. With that method, I'm able to crank out 12 of those stay bolts that are all essentially identical in a pretty modest amount of time. In fact, I lost count and I made one too many, so I did a little inspection on all of them and rejected the worst one, which was about half of that too big. Now onto the stayed nuts. These I mass produced in a very similar way, but a slightly different technique. Because these are very thin, I can make multiples in a single position of the stock without having too much stick out. So these I'm doing entirely incrementally. Each tool moves down to a different Z position on the axis, and I'm not re-zeroing anything. I've also pre-drilled and pre-tapped a batch of them at a time, as you can see there. Basically, however long your tap is, you can make that many of these nuts at a time. These are even quicker than the bolts, honestly. This goes really quickly, especially if you speed up the footage. But just don't reverse the footage, because then you lose progress, and that's really demoralizing. These nuts are a bit of a Kozo-ism also, actually, because normally the stay bolts are just straight up dowel pins. They just go through the two layers and you solder both ends. But he makes these nuts for the other end to help hold them in place during the various operations that we're about to do. So it's a nice design. It is a little bit fussier than traditional. Now I can go back and finish drilling the holes because I know that the drills that I'm using are going to make a good fit on the bolts that I made. So I center drilled all those positions and then once again went all the way through with the drill. Okay, let's do a little test fit here. This is going to be a complex silver soldering operation, so I want to make very sure that everything is going to go together nicely. So a dry fit is definitely in order. And I did find that I needed to, for example, chase the threads on all the nuts, get them to fit really easily, and make sure everything's going to be clean and easy to assemble when it's covered in flux and you can't get your hand in there very easily and so on. Not ideal conditions here, so I need to make this as easy as possible for silver soldering setup. The stay bolts are intentionally close to where the outer crown sheet starts to bend there, and Kozo has you cut down the tops of these bolts for this reason, but curiously, mine actually fit anyway, even without the trimming, so I wasn't sure if it was necessary, but I decided to go ahead and do the trimming anyway because it is very close, and having the trimmed bolts there might make them easier to solder, and there might be other reasons for this that I don't understand, and I'm not in a position of experience sufficient to challenge Kozo's design on a detail like this. So I set it up on the mill. I've got this little aluminum V-block that is great for holding small parts like this. The shanks on these are not a standard size that I have a collet for, but this worked actually very well. And thus 6 of the bolts were milled down with a flat spot like this to fit along the seam of the outer crown sheet. One final dry fit here just to be absolutely sure everything is going to go together easily and correctly because I can't take any chances. This is the most difficult silver soldering step on the whole boiler, I think, so I want to make sure I'm doing everything right here. That looks good, so nothing to it but to do it. I'll set it up on the hearth here, and I'm going to flux all of those areas, of course. Kozo has you do the heads of the bolts first, not the nuts, not the whole assembly all at once, which would be very difficult to get right. I think that's a smart decision on his part. So the bolts all go in there, and then the nuts go on the bottom, and the nuts are unfluxed and don't get solder. They're just there to hold the bolts steady while silver soldering. Fun fact, on the second set of these bolts, I forgot to put the nuts on, and that was actually fine. They didn't move, but the nuts are a good idea. Then a little bit of silver solder goes on each one, as is usual for the Kozo method of silver soldering, which works extremely well. And in we go with the torch. This is actually the other side. I forgot to record the first side, so I'm showing you this one, but they're both the same. And you'll note I'm using the big tip on my torch now, the biggest one I have, because at this stage, every joint requires heating up essentially the entire boiler. So you got to use a big torch for this. And I've learned my lesson on the insulation. If you watched my previous videos, I think it leads to damaging older joints. So I'm leaving the rest of the boiler exposed so that it can radiate a little bit and those joints will protect themselves. But this actually went really well. It's a pretty easy set of joints. They're in a good position for soldering, and it was a pretty straightforward case of heating them up until the solder flowed. The bolts directly under the torch flow first, and then the rest of them are close when that happens, so I just shift the torch over to each bolt in turn, flow it, use the scratch rod to make sure there's a good seam all the way around, and Bob's your uncle. I was pleasantly surprised by how straightforward this was, but don't worry, my fears about this being difficult will be confirmed here soon enough. That one stay bolt on the corner there I didn't like after I was done heating, so I went back in real quick while it was still hot, and I heated that up again and added a little more solder on the corner of that one there. I just globbed a little bit in there very ungracefully and then heated until it flowed and scratch rodded that around. That may not have been necessary, but I just didn't like the look of that one bolt there. After fluxing and washing, things are looking pretty good here. I'm pleasantly surprised by those joints. They all seem good. I don't see anything there that would be of concern as far as having a solid joint. That was done on both sides, and now the tricky part, the inner stay bolts, or the stay nuts if you like. For this next step, Kozo recommends you build a heat shield because we're going to be torching the inside of the firebox, and there's a lot of risk of damaging the foundation ring while doing that. So he recommends a piece of steel sheet metal like I've got here, and I'm going to cut this to size over on my little sheet metal machine, which I'm quite enjoying. As long as you stay within the rather low limits of this machine, it does very well. The idea here is we're going to shape this piece of metal to fit around the foundation ring to keep the torch flame from hitting it directly. Because what I've learned here from Kozo and through my experience building this boiler is what really tends to damage old joints is not the conduction heat from the copper in neighboring joints. It's really when the torch flame is directly hitting old joints. That's what you want to avoid. So this piece of sheet metal here shields that without insulating the boiler, which might cause those joints to fail for a different reason. Let me pause right here and explain this one more time because I know people are going to ask, no, you can't use a smaller torch to avoid damage to older joints. You have to use a big torch because you need volume of heat, not peak temperature, volume of heat. If you use something like acetylene, which is very, very hot and works on a small area, you'll actually melt the materials before the joint actually gets hot enough to flow the solder. I know because I've done it. So it's counterintuitive, I know, but you have to use a huge torch and then just mask off specific areas that you don't want to get touched by the flame. But the large torch is needed to counteract the heat sinking effect of the materials. Now this steel is galvanized, which is not a great choice for this, health and safety warning. So I am wearing a respirator though. I wear a respirator whenever I silver solder, and I have the roll-up door partially open, and I've got a fan in the back putting positive air pressure out of the shop. So everything is very well ventilated, and again, I'm wearing a respirator here. So keep that in mind. You really don't want to heat or weld or otherwise abuse things that are galvanized because zinc fumes are extremely, extremely bad for you. I've also got ceramic wool down in there to protect the fire tubes and other joints that are inside the firebox, so I'm trying to make sure that only the stay nuts there are going to get the torch. And in hindsight, I should have put actually more heat shielding around the foundation ring. Kozo says you only need that one piece on the bottom edge, but I think covering all the foundation ring would have been a very good idea, as you'll see here in a little bit. I've also got the solder positioned on there. As you can see, I've got a piece at the base of each stay nut, and then there's a little piece on the top of each thread that's supposed to flow down and seal the threads of each bolt. Again, this is all from the book, and if you do it right, in theory, it should work very well. This actually goes really quickly because the firebox, of course, contains the heat, and so things get hot in there very, very fast, and it did not take long at all for these stay nuts to flow. And it looks like that sheet metal did a really good job of protecting the foundation joint. There's no signs of any heat getting to it there. It is, however, covered in white powder, as you can see, and I think that's the zinc. So again, I probably shouldn't have used galvanized sheet metal for that, but it was what I had, and with the respirator, I think it was fine. So pickling once again and cleaning up, and this looks okay. There's one or two of those stay nuts that are a little suspect. Some of the solder maybe didn't flow as well as it should have, but I'm not going to risk trying to fix things right now because we're mere hours away from the pressure test, and every fix comes with risk now, so better to wait until you know something is a leak before you try to fix it. Speaking of which, I'm pretty sure I damaged the foundation ring right here on those stay nuts. That does not look like soot. Those dark spots there are almost certainly gaps. In that footage, you can see that the torch is hitting that area, so I really should have, again, put more shielding around there, and in hindsight, I'm a little surprised Kozo doesn't recommend shielding the entire foundation ring. But for subsequent operations, if I need to work in there, I definitely will. Now it's time for the front tube sheet. This is it, the final piece. Kozo recommends a chamfer on the inside edge here to help the solder flow down in there. He recommends filing it, but who's got time for filing? A deburring tool on copper actually works really well to create a chamfer. It's just like carving butter. I did a bunch of mechanical cleaning here as well. My pickle bath is not big enough to put the whole boiler in, so I've only been pickling one end at a time, whichever end I'm working on. But that's mostly the back end, so the front end here has not been pickled nearly as much, so it's got a lot of soot from the torch and other crud accumulated on it. So pickling was not quite enough. I needed to do some mechanical cleanup here to prepare this joint for soldering. Now let's do a test fit here and make sure that everything is going to go together nicely. Again, I want to make sure that the dry fit is all good before I start trying to flux things up and solder. That fits on there very nicely. It's actually quite satisfying to push that on there. But there is a little bit of a gap on one spot that I'm not super happy with, right where the seam is at the bottom. It's a little bit out of round, so I just tap that joint in a little bit. Again, everything's pretty soft here, so it's not difficult to push the metal around a little bit if needed. And I think I've got a good joint everywhere now, so let's do this. Let's get ready to solder this thing. Flux goes on both sides of the joint as usual. Pretty exciting moment here. This is the final piece of this boiler before we have to start probably fixing leaks and otherwise making it actually sound. But at least the structure will be done once this piece is in. Now, Kozo has you do this in 2 stages. I'm not 100% sure why, but he has you do the outer seam of the tube sheet first, and then all of the pipes and tubes there in the center as a second step. Again, not sure why, but I'm following his directions because I'm sure there's a good reason for it. I'm tapping this nice and square here. I want to make sure that the tube sheet is as square as I can get it anyway to the shell. The smoke box and some other features of the locomotive here do mount to this tube sheet, so I want to make sure that it's going to be straight when we're done here. I only get one shot at this. Touch up the flux as usual, and let's get some solder on there. I've learned along the way here that it's easier to put a lot of little pieces of solder on than one giant one, and trying to make a giant one fit and sit properly. So lots of little ones is the way to go. And then pointing the big torch at the end here is all that's needed. Then my camera battery died, so you'll have to take my word for it that that went great. So I pickled it and cleaned it up once again and got set up here to do the final few joints here. That's the tubes and the steam pipes. Kozo has you plug the tubes with ceramic wool and stuff that wool down a couple of inches. He says this is not about protecting the joints on the other end of the tubes, it's to make sure that the tubes don't expand more than the tube sheet does. I'm not entirely sure how that works, but he says to do it, so again, I'm going to follow his instructions because he has never let me down yet on this project. And yes, I'm standing on a stool here to get the height required. I'm not that tall. I wasn't sure exactly how to heat this joint safely because I would think that damaging the seam that we just did around the front of the tube sheet would be a serious risk here, but it didn't actually seem to be. I think because the tubes and the steam pipes heat up so much more quickly than the boiler shell does. The boiler shell is acting as a heat sink, and I think that's protecting the main tube joint. So I think that's why this works, because it was actually quite easy to heat this up to where the tubes and the pipes were flowing, but the joint around the outside was showing no signs of getting too hot. That Kozo knows what he's doing when it comes to order of operations on silver soldering. Well, that's it. It's a boiler-ish. Let that cool down, a final pickle and wash, and well, that is basically it. I'm going to do an inspection here on the front tube sheet, make sure that I don't need to do one more heating on that, and that seemed to go really well. Those joints actually look really good. Those were easier than I expected as well. Possible gap there? No, that's just soot. Yeah, this thing looks really good, I gotta say. I'm really quite pleased with how that all went. Well, there it is. The structure of this boiler is complete. I know the boiler is not fully complete because I know for sure there's at least one leak on that foundation ring. I'm almost positive, and I'm pretty sure at least one of those stay nuts is probably leaking inside the firebox. Definitely some sketchy stuff in there. So we won't know for sure until the pressure test though. Again, it's not worth trying to fix anything yet until I know for sure they are leaks, because at this stage, every time we put the torch on this thing, we risk damaging an existing joint. The risk is real, so we got to make sure that we need to fix something before we attempt it. Well, that is all the time I have for you today. We will find out next time if this thing passes a pressure test. I'm excited. I hope you're excited. Please stay with me. And thanks so much to all of my patrons who've made it possible for me to get this far on this crazy project. I'm really excited. I hope you are too, and I'll see you next time.